It's a great pleasure to welcome David Spergel, who's going to, from Princeton, who's going to tell us about cosmology after Planck's small-scale CMB experiments. Thanks.
Well, I signed up to give a talk on cosmology after Planck's small-scale CMB experiments. Then I looked at the program and realized that was basically a linear combination of the titles of the 4 previous talks. So decided to switch somewhat and replace one talk with actually what will be 2 talks that are actually quite distinct, but I thought I wanted to touch on both things. One is kind of revisiting Planck and looking at an independent reanalysis of the Planck data that René Lozic, Raphael Flauger, and I have been doing, where we've taken the publicly released data and tried to recompute parameters and seen what conclusions we've come to. The second is I thought it would be a nice opportunity just to give people a quick update on what's going on in the United States with WFIRST and AFTA. As some of you may know, we were given as a gift a 2.4-meter Hubble-sized telescope with a wide field of view and asked, would this be useful for dark energy studies, for other astrophysics? We came back with a positive conclusion. And I just want to give people a sense of where that's going to, what's going on with that, because looking ahead in cosmology, at what we will be doing for precision cosmology in a decade from now. I think a very important part of that picture will be work many of us will be doing using lensing to characterize a large-scale distribution of structure, other measurements of distances, and I think what will likely be the 3 key observational tools we'll have for that will be LSST on the ground, Euclid in space, and I think many people here are very familiar with Euclid. But another part of that story will be this WFIRST AFTA mission, so I want to talk about that. I just want to begin by reminding people of the remarkably consistent picture of the CMB. Here it is in the same color scheme. And all the important features like the SH appears in all of them. And this consistent picture also appears when you look at smaller scales. If we go, look at the ACT data. Let me just pull that up, sorry. Thought I had it set up to pop up. This is the Planck sky map. This is the ACT sky map on the same region. You see the same fluctuations at the same location. And this is just a real space representation of what Joanna Dunkley showed of the data being remarkably consistent. And then looking at this is looking again at the consistency between WMAP and Planck. And this shows the cross-correlation between the 100 gigahertz Planck data with its 217, WMAP 94 gigahertz with 217, shifted by this about 1.2% in amplitude, about 2.4 to 2.7% in power. This factor, we need to normalize it. And I think you can see once you've done that amplitude shift, which we're all working to understand, the data sets are remarkably consistent. And you can see this is on the same patch of the sky. They agree very well at low multiples where WMAP is cosmic variance limited. And out here, you can see that they're consistent. And Planck's lower noise allows you to get this precision measurement of the power spectrum, really all the way out, to 2,000 to 2,500 range. And this figure here is flashing back and forth between the pre-release and Planck measurements, and you can see overall they're remarkably consistent, but now with Planck filling in this part of the spectrum with much higher precision. And another way to look at that is that the parameters are mostly consistent, and I'll talk about this a bit more in the next few minutes, but if you look at, here are the kind of 4 key parameters I want to focus on. This was our best estimates pre-release of parameters from WMAP plus ACT, and here's the Planck plus WMAP polarization numbers, and all these parameters tend to be kind of correlated with each other, and there's basically a shift of about a sigma in the WMAP parameters, in the Hubble constant going down, the matter density going up, ns going down a bit. And that shift, on one hand, is consistent within the two data sets, but when you look at other astronomical data, and this is something George talked about, you start to see interesting deviations. And this is from the Planck paper. This figure's been corrected by the Planck team because the neutrino mass was not included. When you do that, the red curve comes down a bit, and they kind of kiss, but there's still a significant difference between the sigma 8 omega matter value measured from the CMB and those inferred by clusters or gravitational lensing, sort of at the 2 to 3 sigma level, depends exactly what data set you look at. The Hubble constant is inferred from Planck is now, with that 1 sigma shift down, it's now getting a little uncomfortable. And there's, the high amplitude of density fluctuations are also a little high relative to a lot of the ground-based results. And I think this suggests one of 3 interesting possibilities. The most interesting is that this is pointing to new physics. And as the data improves, this 2 or 3 sigma deviation becomes a 5 sigma deviation, and we identify the new physics, whether it's neutrino sector or something else that's going on here. The second possibility is that there's systematics in the astronomical data. And, the astronomical data sets are more complex, and that may be what's going on there. But I think it's also worth considering, are there some systematics in the Planck data? And this motivated us to go look at the Planck data. It was also motivated by some of the trends seen in the Planck analysis, things like the dependence of the parameters on, particularly on the 217 cross 217, driving the data, and some funny features in the 217 power spectrum. You see this is the deviation of the 217 power spectrum showing this feature round of L of 1800. My understanding is that it's now understood to be a systematic and is improved in later data analysis. And there's also a number of null tests. So if you look at, this is a comparison, this is from Planck paper 6, of the power spectrum measured from different detector set pairs. And at 100 and 143 gigahertz, they all pass the test. At 217 gigahertz, there's a number of detector set pairs that don't pass the test, and you see deviations at the level of 20, 30 microkelvin squared in the differences. So that motivated us to go look at the Planck data and to see what could we do with the publicly available data. So we took the publicly available data that doesn't include the detector set map, so we can only measure cross spectrum from different seasons. That has the advantage, actually, of when you're looking at 2 completely independent seasons, any systematics tend to drop out. One of the things we do in our ground-based analysis, for example, with ACT, and I believe the SPT team does a similar thing, is you just take observations measured on different days and always work with cross correlations. In doing that, that reduces the amount of data available, so it blows up the errors a bit. So we want to use more sky, so we also want to make use of the 353 and 545 Planck maps for cleaning. And they turn out, as I'll show in a moment, to be remarkably good at cleaning up the sky. You can see that in things like the component separation analyses, but they're a very powerful addition to the lower frequency maps in terms of characterizing what's going on. And in doing this analysis, we basically stuck with the CAM likelihood package. Of course, since we're using different data sets, we had to recompute the covariance matrices and plug them in. So first, let's just look at, just within the CAM likelihood, the sensitivity of parameters to the data included. So if we remove the 217 gigahertz data from the Planck analysis, so it's just taking the CAM spec as is, let's see what happens when we remove this. This is actually looked at in paper 15 in the Planck analysis, but we redid it here. And you can see it shifts all the parameters from these values here to values that are almost identical to the WMAP 9 plus ACT results. So it suggests, whatever difference we're seeing is driven by 217 cross 217. And that's the spectrum that, we saw these problems in the detector sets of the Dull tests. The cleaning lets us use a lot more sky. Show that in a couple ways. This is just the effect of cleaning with 545. So what's shown on the left is the power spectrum computed with different frequency combinations. Usually in the Planck analysis, you see the bottom couple here, the ones in the triangle shown. Because these other combinations have so much foreground in them, you can't use them without a lot of foreground modeling. But just using the dust seems to correlate extremely well, have a relatively close to constant spectral index across this, the high latitude sky. Because all we did here was find what linear combination minimizes the variance, remove that one number from each of the maps, and this is the cleaned up spectrum. And you can see even the 353 cross 353 spectrum, which started out way up there, comes down to here. So the maps clean up very nicely. Given that, we decided to use them to use larger sky. What we did to minimize the contribution of the 353 and the 545 maps to the noise is we took one map, which was clean on 217 or 145 and 100. We did the same thing with all of them. That was cleaned with 353, one map that was cleaned with 545, and cross-correlated them to reduce the contribution to the noise. And we computed the spectrum. This is a mask shown above that's very close to the Planck mask used in the analysis of the 217, except for since we only have the cross seasons, we have to throw out the region that was only observed at one season. That's this ecliptic strip here. You can see it come across there. Then we also moved to a much larger sky coverage here, and the two spectrum are shown here. By, of course, going to larger F sky, this is about an F sky of about half the sky, you get smaller errors. And this is the difference between the two spectrum measured at 217 as a function of L, and there's just no difference, right? So this is a lot like the double differences that are done in the Planck analysis, but now we're doing this on the clean maps, and there seems to be no evidence for galactic foregrounds. So we then take these new spectra, plug them into the likelihood code, and see what comes out. And here's on top is the clean spectra with its best fit model. Here's the Planck CMB, the released ones and their best fit. And you can see it's a bit better fit, particularly around the high L region. And when you look at what it does to parameters, it shifts the parameters. So the black curve is our analysis with 217 and without 217, giving a bit larger, the sort of 1 sigma higher Hubble constant. Very consistent with the Planck data, the Planck analysis without 217. And so all this shift seems to be coming from the detector set crosses. And with this, you see even less evidence for new physics. The neutrino mass likelihood curve gets closer to 0. The best fit and effective now centered around 3. Things get even more boring. Though, if you like m squared phi squared, this 1 sigma shift now moves m squared phi squared more deeply into the 2 sigma allowed region. So what's going on here? Why is this parameter shift happening? It seems to be driven by 217. 217, mostly the difference in the 217 detector sets. When we went through this analysis the first time, and I talked about this at Davis, I emphasized the cleaning because I knew that was one of the differences. But now that we've run through the likelihood code where we take our maps without cleaning stick them into the code, you actually get, in terms of omega cold dark matter and ns, this is the Planck with 217 in the x. Up here is the Planck release spectra without 217, very close to what we get with the cross-season spectra, either with or without 217, when we do the cleaning. When we don't do the cleaning and just fit with the code, we actually even get a larger omega CNS. So it's not the cleaning that's making the difference, it's the detector set pairs. And another way of just looking at the changes is if you look at the difference in the spectrum that's released once you remove the best fit foreground models, the 217, 217 is a bit low in the upper plot compared to 143, 217. When we go through our analysis, we get one that's more consistent with the 143, 217. These shifts are all 1 sigma shifts in parameters. And some of this is driven by the fact that you're adding extra data. And we can't tell from what's there, what's released, whether this is pointing to some systematic or just the effect of adding extra data. The thing that I hope we encourage the team to do is release the detector set maps, because that will allow external checks that the deviations with astronomical measurements, I think, are interesting enough and important enough that even at this kind of 1 sigma level, it's worth trying to understand them. And of course, all of this is going to be a lot clearer when we have 5 seasons, right? So my experience with WMAP was the more data we had, the better we understood things. Also, one of the things we found was the more data we had, any 2 sigma anomaly just tended to go away. All the things that seemed to be a little bit off, with more data, things seem to improve. So I think we're all looking forward to seeing the 5-season temperature maps and then next the polarization maps and see what that shows. I think perhaps the overall takeaway from this is first, having an opportunity to work closely with the Planck data, you see the remarkable quality of the data. And I'd actually think with the 343s and the 545s, there's an opportunity for the Planck team to make more use of them, because I think they can allow you to use a larger f-sky. I also think, at least from the data that's released, there seems to be some issue in the detector sets crosses in the 217s. And if those maps are released, I think that could be understood better. And I think this data is so important to cosmology that it's really, I hope we're providing a service by coming back and revisiting the data. One of the things that we certainly benefited from in the WMAP team was having external analyses, people coming up using different techniques, and we certainly learned from what other people did with WMAP data. So now let me change hats completely. I'll move into my Washington, D.C. mode, put on a jacket. I really ought to put on a tie and nicer pants, but this is all I have with me. And talk a little bit about this, now, as I say, now for something completely different. Story of what's been going on with this telescope. So this was has been so far a very interesting thing to be involved with. I got a phone call about 1.5 years ago from folks at NASA headquarters saying, we can now talk about the fact that we have a 2.4 meter telescope that was given to us by another agency. As some of you may know, NASA is our 3rd largest space agency. There's an article in the Washington Post 3 or 4 days ago that actually gives out the budgets of the other agencies, and it is indeed the 3rd largest agency. One of the other agencies had a telescope from a canceled program. It's a 2.4 meter telescope, optical telescope assembly. It was designed to look down, and it's a wide field telescope. and they asked us, would this be useful? The fact that it was available suggests to me one of two things. Either the US government feels you can learn enough by listening and you don't have to look anymore, or that they have something better. We had a couple workshops on this, and after some stimulated NASA headquarters to ask us to look at this, and NASA put together a study team to spend last year looking at what you could do with this telescope, and was it suited for the top priority of the US Decadal Survey, the W-FIRST mission. And we had, fortunately, a very good team of people who worked with us on it, and the same team is now carrying forward, and with a few additional members, to continue to explore this mission. The basic conclusion we came to was, perhaps not shocking, a 2.4 meter telescope is more capable than a 1.3 meter telescope. And that the telescope could be used as a 3-meter astigmat. We were actually the setup we have is only the primary and secondary. The tertiary was part of an instrument that was removed. And that we concluded that not only did this meet the requirements set in the Decadal Survey for the science, with the larger aperture, it exceeded it and enabled a wide range of new things. And one of the things that was quite interesting to look at, and we're continuing to explore now in more detail, is having this telescope meant we could put a coronagraph on it. One of the things that was considered by a number of studies in the US Decadal Survey was flying sort of a 1-meter class coronagraphic mission. And the cost of that turned out to be around $1 billion, and the science return was somewhat limited. And this was not, while there was a lot of interest in the exoplanet community, it did not emerge as a top priority, particularly given our limited budget. But given that we have the telescope already, and it turns out that there are coronagraph designs, and we're focusing right now on choosing the exact approach we want to use for the coronagraph, the larger telescope and having it available makes it relatively inexpensive to include a coronagraph and do interesting exoplanet work. So the basic plan is to have a wide field instrument that will operate the near infrared, right? So in contrast to Euclid, which is going to be doing its imaging and lensing work in the optical, this will be operating in the near infrared, 0.7 to 2 microns. Right now, the 2-micron cutoff is set by the fact that the telescope was designed to look down and operate at a warmer temperature. We're now studying whether or not we can run it cooler. We're hoping to push that limit to 2.4 microns. The plan is to have about 0.28 square degree field of view, 18 H4RG detectors. They're the next generation IR detectors, 288 megapixels. And our current plan is the current design is 4 filters. We're thinking those details are something that's under study, what we'll do with filters. Plan to use a GRISM and have an IFU on it for spectroscopy of the supernova. In addition to that, we'd have a coronagraph. Now, the coronagraph operates in the optical from about 400 to 1,000 nanometers. We're looking at achieving a contrast of about 10 to the 9 in the coronagraph. 10 to the 10 is what people hope to do for Earth-like planets. So at 10 to the 9, we're looking at not just detecting, but characterizing the atmospheres of massive exoplanets, Neptunes and Jupiters. And if we're very lucky, and there's an Earth-like planet around, Alpha Centauri or a handful of the nearest targets, perhaps look at that. But we're really designing it for the giant planets. One way to look at this is to think about every HST picture you've seen, and to realize when you've got this field of view, it's 200 times the field of view. So every time you've pointed Hubble, you now get 200 times the area. And I think this enormous area in the infrared gives us the ability to address many of the outstanding questions in cosmology and astrophysics in general. A lot of the questions we identified in the Decadal Survey, and we've been talking about in the meeting here. So the plan for the survey is to carry out a deep survey. In many ways, this is very complementary to Euclid, right? Euclid's going to cover of order 20,000 square degrees. And while Euclid's quite deep by the standards, as we'll see, this will go much deeper on a smaller fraction of the sky. So the plan is to look at about 2,000 square degrees of high latitude sky, about 500 million lens galaxies. So we're now looking at about 70 galaxies per arc minute squared. That's a much deeper lensing map. You could look at about 20 galaxies per arc minute squared when you're looking at LSST or Euclid. Looking at about 40,000 massive clusters. We'll do, with the IFU, we'll have high quality supernova data, carry out a large supernova survey, do spectroscopy going out to redshift 3 using a combination of H alpha from redshift 1 to 2 and oxygen 3 from redshift 2 to 3, and also do things like redshift space distortions to look at velocities. When we looked at the parameters, all these methods are giving us 0.1 to 0.4% precision. There have been previous studies of doing WFIRST with smaller telescopes, and the basic conclusion we came to was bigger is indeed better. We also felt that it was something that was quite, as I mentioned, complementary to Euclid, in that we're going deeper, covering Euclid for, say, spectroscopy. This is the NP you're looking at around the BAO peak. Here we're going to an NP of order 1, pushing out to redshift 3. We'll also do very interesting things for exoplanet science, both carrying out a micro-lensing survey. Here's the range. Sorry, this didn't reproduce that well. In mass, semi-major axis covered by Kepler. For lensing, we'll cover this region here. For exoplanet imaging, we will, so here's a better version of that plot. So for microlensing, we're looking at discovering about 2,800 planets, given the current values from Kepler, and just extrapolating them out. The combination of the two will provide detailed kind of statistical sampling of the distribution of exoplanets. In addition to the microlensing work, we'll also do imaging. This sort of shows the region that this will push to in sensitivity compared to what's being done from the ground and what's planned from the ground with 30-meter telescopes. Also looking at what one will do with debris skies imaging. My time's running late, so let me just quickly mention that one of the things that will be quite interesting here is to look at the distribution of dark matter. There have been remarkable results coming for HST on things like the CLASH survey, where we're looking at the distribution of dark matter. The thing to think about here is we will carry out a survey like CLASH, but over 2,000 square degrees. Right? So you'll have Hubble quality imaging, but now with 200 times the field of view. And you get these detailed arcs. Oh, keep going. And that's just a small part of the view. Other things I think that will be quite interesting for this, it'll be quite complementary to JWST, because we'll be surveying the sky, large areas of the sky. So you'll be able to find, for example, with current extrapolation, tens or hundreds of galaxies out to redshift 12, 13, 14. You'll see these things in near IR, and then JWST will follow up on this. So this will be a great finder telescope for JWST for a number of applications. It'll also be, I think, in terms of its astrometry, a very nice complement to Gaia. Because where we will do multiple imaging, if our plan is to spread the imaging program out over the life of the mission, and that gives us enough baseline that we can do astrometry about 4 magnitudes deeper than Gaia. Lower, we suspect our systematic limit will not go as deep as Gaia. So for bright stars, Gaia will be much better. But this will tie to the Gaia frame and let us do things like look at motions of main sequence stars in tidal streams of dwarf galaxies, and be able to do things like constrain the amount of substructure in our dark matter halo, which will in turn give us insight into what the dark matter is made of. I'm reaching the end, so let me conclude by just noting for some things like, here's the M31 survey that was done being done by HST right now, led by Julianne Delcanton. That survey took 432 pointings to survey M31. Our plan is to spend at least 25% of the time doing general astrophysics, and you can do projects like that in two pointings. It'll be quite, I think, we'll have a very nice map of the sky with the combination of LSST, AFTA, and Euclid. So in terms of sensitivity, it very nicely complements LSST and represents sort of about a factor 100 improvement on the survey sensitivity of Sloan. You're going about 100 times deeper with LSST, about 100 times deeper here, but now covering, because of the observation in the infrared, almost an order of magnitude in wavelength range. And in terms of image quality, Euclid will provide really striking images in the optical of galaxies at almost the same resolution. This telescope will provide near-infrared images. So this looks very promising. We presented this to headquarters, put on the jacket and tie, talked to the NASA administrator, congressional staff, OMB, and we've got this into the language in both the House authorization bill. So we got the Republicans to like it. We got the Democrats to really like it. So there's $56 million in the Senate authorization bill. When will it launch? If JWST stays on budget. So far it's been, since the rebudgeting, they were given enough budget at the moment that looks reasonably, that is possible. This would fit into the NASA budget profile for astrophysics, and the current plan by the astrophysics division is to go into phase A in 2017 and launch in 2023. The optimistic scenario is if that Senate language is adopted in the House-Senate compromise, and who knows what's going to happen in Washington with the budget this year, that would actually schedule a 2021 launch. So I think either way, this is something that's likely going to happen in the Euclid LSST timeframe. So when people are thinking about what's coming, I think this is likely an important part of the picture. As many of you know, NASA is a minor partner in Euclid. I think one of the things that worked very well for the US community, and I think also benefited Planck and also Herschel, was to have US participation in Planck and Herschel. The same thing I hope will happen with Euclid. I believe that there will be opportunities, if there's interest on the ESA side, for European participation in WFIRST, this after WFIRST mission. Right now, the Canadians and Japanese are both sending observers to our upcoming meeting next week. And the reason for this advertisement was a hope to stimulate interest in Europe and potential European involvement in the mission. Let me stop there. Thanks.
Okay, it's inspiring to see that cosmology will continue to be a data-driven field. Now, I'm sure there are some questions about the talk. I mean, I realize it's lunchtime, but perhaps the Planck people want to respond a little bit. Oh, George.
Right. So, I mean, what we did in terms of sky coverage and cleaning was, I think, very, very conservative. And in fact, you can use the same methodology and push sky coverage with the template-based and,
right,
mass difference dust approach. The thing that worries me about using 353 and 545 for cleaning is do you really know what is going on with the unresolved foregrounds? Because the likelihood is being pulled by the high multipoles. You've got high signal to noise. So if you get it slightly wrong, if you get the cleaning slightly wrong, it will pull parameters. I mean, we're very, very close, right, in the numbers, but we have to worry about
Well,
what's actually going on.
We get the same numbers, basically, whether we use the cleaning or not. And we get the same numbers whether we use the larger F sky or the smaller F sky. When we don't use we use the smaller F sky and use the Planck likelihood without the 217 detector sets. We get the same numbers we get this shift of a sigma to larger Hubble constant. So it doesn't seem to be the details in the cleaning. We see the same spectra whether we clean with 353 or 545, and in both cases all we see are point sources. Now, one of the nice things about doing cleaning with a higher frequency is, half your sources will have spectral indices above the mean, and half will have spectral indices below the mean, which means half your sources will be, residuals will be positive and half will be negative. That leads to only a Poisson-like term. That doesn't lead to a clustering term. So you're not very sensitive. We actually, when we try to do the fit, see no evidence for a residual clustered term. There's just a Poisson term. So it actually simplifies the analysis that way.
So do you fit a clustering term?
We try fitting a clustering term. The best fits around 0, so we've done it both with and without. Doesn't make a difference, really.
I think what would be interesting would be to, we could compare spectra to spectra.
Yes. Oh, I have a comparison of the spectra at 217. I flashed that quickly. No. Yeah, this is the one. This is comparing to 143 cross 217. But the difference is mostly out here and a bit here. The spectrum is a bit closer to the 143 cross 217.
In the nominal mission analysis, where there was marginal evidence of problems at high multifold, it was the 143217 spectrum that was the one that fitted least well.
I guess the null tests that were reported were all for the 217-217s. That were described as the 3 failures of the null tests were described as 217-217s.
Quick comment.
Just to add 2 points. First, about using the 353. I mean, 353 in the concept of Planck was there for what you did. Why didn't we use it to go a bit beyond what George just said? We have systematics that we did not correct fully, which is this non-linearities of the analog digital converters. Now, we could correct for that up to 217. The first order term, which was just basically gain variation, were corrected. We could not do that for the 353, so we're pretty worried about leaving that. Now, that's done, and that's done properly all through, so we'll see what it gives. Now, about your question about delivering to the community the detector sets and so on, absolutely no quarrel about the principle. In fact, you asked formally that, and the science team has discussed that, and at least my position as a PI and some of my colleagues were on the same line, is that the amount of work to deliver that to everybody, including everything you need as ancillary data to figure out how to use them, will take time. Mm-hmm. And at this stage, it's better than we do that for the new data, the new data set, instead of shifting that new data set by 6 months to do that on the first two. So that was the only logic that we probably serve better the community by doing that directly on the new data than
Yeah, I mean, I think all this will be much clearer with 5 seasons. I mean, I think if there's any, so that's in, but I do hope when the 5 seasons come out, it'd be good to have, be able to reproduce all pieces of the analysis. Yeah, I mean, I was concerned about this issue of whether there was some systematic in 353 or 545, which is why we did the clean one set with 343, one set with 545, and cross-correlated them. So if there was any residual systematic, it wouldn't show up that way.
Okay, well, it really is lunchtime, but Joe, you have something compelling to ask very quickly.
It was just a quick comment as well that looking at this plot, it looks like it's at L greater than 2000. It might be different, but I think the Planck parameters stabilize by L of 2000, don't they?
No, they don't. The shift is, if you take the Planck analysis and run it to look at the cutoff at 2000 and the cutoff at 2500. If you look at the last figure in paper 16, the shift that shifts it. I have the figure here. There it is. Yeah, so this line, this blue line here is for Lmax of 2000. And the Planck is for, this black line is Lmax of 2500. So you can see if you go to 2000, you get the same value of NS that we were getting, not including it. So it's 217 cross 217 beyond 2000 that seems to be playing a significant role.
Okay, well,
And everything goes together, so NS and H naught all tend to go together.
okay, well, today David gets the last word, but I'm sure the discussion will continue. Don't forget, for lunch, you want to sit down, and then you'll be called to the cafeteria, the buffet, I mean. And let's thank David again for a very entertaining talk.